Right, here in problem number 5 and 13.7, we're told that an unevenly heated plate has temperature T of xy at the point xy. Temperatures measured in degrees Celsius and distances are measured in meters. Suppose that T of 2,1 is 135 degrees. The x derivative of T evaluated at 2,1 is 16 degrees per meter, and the y derivative of T evaluated at 2,1 is minus 15 degrees per meter. Okay, part A says to find the linear approximation L of xy to the temperature function T of xy at the point 2, 1. All right, so for the linear approximation, right, we have that L of xy is equal to what? Well, it's the temperature at our base point, which is just 2, 1, plus the x derivative of our temperature function evaluated at that base point times x minus the x coordinate of our base point, which is 2. And then we have plus the y derivative of our temperature function evaluated at the base point times y minus the y coordinate of the base point, and that would be 1. So that right there is the linear approximation. And now, since we know that the x derivative evaluated at 2, 1 is 16 degrees per meter, and we know that the y derivative of the temperature function evaluated at 2, 1 is minus 15 degrees per meter, we then can say this, okay? This portion would be 16, and I'll drop the units for now, x minus 2 minus 15 times y minus 1, and finally, we know the temperature at our base point, right? It's 135 degrees, so this would be 135 plus. Okay, so this is our linear approximation function. And now, moving on to part B, it says, approximate the change in the temperature if we move from the point 2,1 to the point 2.04.97. Okay, so now one way to do this is just to use our linear approximation function we just derived, right? All I'm going to do is plug in the coordinates of this neighboring point. And notice that this neighboring point is reasonably close to our base point of 2,1, so we're not deviating too far away. And so this is going to be what? Well, it'll be 135 plus 16 times, and x is 2.04 minus 2 minus 15 times y, well, that's 0.97 minus 1. So just plugging in there. And now I'm going to write it this way for emphasis. This is 16 times, and this is just 0.04, and then we have minus 15 times a minus 0.03. Okay, now we can go ahead and compute this. It turns out to be 136.09, and I'll put the units in now. 09 degrees, right? So this is our approximate temperature at this neighboring point, 2.04.97. But we're asked to approximate the change in the temperature, not the temperature itself, right? As we go from this base point to this new neighboring point. So now what we could say is this, right? Our change in temperature, delta T, well, this would approximately equal what? It's going to just be this approximate temperature we just found at our neighbor point minus the base temperature of 135 degrees. Okay, and so there we're getting an approximate change of 1.09 degrees. Okay, now that's all fine and good, and we are done with the problem. I mean, we've answered what it was asking us to do, and this is all good and fine. But I do want to point out one thing here, just in light of some other things we've been talking about, right? This thing that we just found is really, so this thing right here, the 1.09 degrees, is really just dt. In other words, we just computed the differential change in our temperature as we move from our base point to this new point. And why is that? Well, let's go back up to this expression here. Looking at 16 times the 2.04 minus 2, that's really just 0.04. So put another way, right, this 0.04 is nothing other than dx. It's just our little change in x. And what is this, the minus 0.03? Well, that is just the dy, right? That's just, right, we've decreased y by 0.03 units, okay? And so then what's the 135? Remember, that was just the base temperature here, and what we wound up doing is just subtracting the two. So what is this thing here in total, right here? That is just our ty at 2,1 dx plus our ty at 2,1 dy, and this really was by definition the differential change in the temperature, right? And this 135 wound up getting subtracted anyway, so this really is all just kind of coming back to this idea of differential change, which is just telling us the change along that tangent plane approximation. All right, great. Well, let's stop there. That does it for this question.